My name is Peter Selinger, and with my co-authors Frank Fu and Kohei Kishida, I would like to tell you about linear-dependent type theory for quantum programming languages. The goal of this research is to develop techniques for formal reasoning about quantum software, and we do this via the theory of quantum programming languages. In this talk, we want to focus on high-level languages, and by a high-level language, I mean a language in which an algorithm can be described at a similar level of abstraction at which the algorithm would normally be described in a research paper. Formal methods are even more important in the quantum setting than in the classical setting because basically you can't debug a quantum program. It is not possible to just stop a quantum program in the middle of the computation and examine its state. So formal verification is perhaps the only way to ensure the correctness of quantum software. The programming language that we've developed over the last 8 years or so is called Quipper. Quipper is a functional programming language. It's embedded in Haskell and it's quite practical. We've implemented several different algorithms in Quipper, including some quite complicated ones from the literature. And some of these algorithms produce trillions of gates. Quipper is embedded in Haskell, and while this makes it quite practical, unfortunately Quipper is not type-safe, because there are two features that Haskell doesn't have. One of these is linear types and the other one is dependent types. And both of these would be necessary if we wanted to make a type-safe version of Quipper. And so for the past few years, we've been working on a family of programming languages that we call ProtoClipper. ProtoClipper is basically our attempt to formalize a meaningful fragment of Quipper. It's a family of languages because in the beginning we started with a small core, and we're using this as a platform to experiment with adding different features to the language. And the goal is that ProtoClipper will eventually be as useful as the real Quipper. So, the first thing to understand about Quipper is that Quipper is a circuit description language. So it's a language for describing families of quantum circuits, where the families might be parameterized by some kind of data. And you can describe circuits at different levels of abstraction. The lowest level of abstraction is when you describe the circuits one gate at a time. In Quipper there is a type qubit, and a value of this type is essentially a pointer to a place in a circuit where a gate could be appended. And as the term M evaluates, every once in a while it says, please apply the gate G to qubits K and M. The pointers K and M will be used up, and there will be new pointers, say K prime and M prime, corresponding to the outputs of the new gate. But as it turns out, describing circuits at this very low level of one gate at a time is not at all how people describe quantum algorithms in the literature. Rarely do you find a paper in the quantum computing literature that says, first apply a Hadamard gate, then apply a control NOT gate. Rather, these algorithms are typically described at a fairly high level. For example, someone might be telling you, such and such problem can be solved in polynomial time. Therefore, there exists a polynomial family of classical circuits for this problem. Using a standard trick, we can turn these into reversible quantum circuits. And then we apply another method to the circuit, for example, phase estimation. And what it means is that most of the description of a quantum algorithm is usually by describing transformations on entire quantum circuits, rather than talking about individual gates. And in Quipper, we therefore want to be able to express these ideas of operating on whole circuits at a time. So an example of a circuit level operation is take a circuit and then reverse it. Okay? For example, many quantum algorithms take the form A, then B, then A inverse. So you don't want to write a program to compute the circuit A and another program to compute the circuit A inverse. Rather, you want to generate A and then invert it. And the way that these high-level operations are provided in Quipper is via these constructions called boxing and unboxing of circuits. So if A and B are quantum data types, then A arrow B would be the type of functions from A to B. And when you run such a function, it might issue some gates and compute a quantum circuit. But when you want to treat that circuit as data rather than a function, then you need to box the circuit. So box is an operation that takes a circuit generating function and turns it into a circuit that is data. And the way that this is handled in the operational semantics is this. If you're evaluating a term, which maybe holds several references to qubits in the current quantum circuit, then when you come to a box operation, then the current circuit is put aside and the term inside the box operation is evaluated in the context of a new empty circuit. And when that term finishes, then the whole circuit is put into a data structure and becomes the return value of the box operation. And once you have this ability to box circuits, then you also have all kinds of things you can do with the box circuit. For example, reversing it, simplifying it, applying a gate transformer that maybe replaces certain gates by other gates, and so on. And some of these will be predefined as primitive operations in the programming language, and other ones will hopefully be definable by the user. Now, when you want to have such a language where circuits can be described either at a low level or a high level, and you want that language to be type safe, then that's not an entirely trivial thing to do, okay? And it turns out that to make a type safe language, it's very important to make a distinction between values that are parameters and values that are states. So let me explain what I mean by that. Because Clipper is a circuit description language, it shares this feature that can also be found in hardware description languages, where there are basically two runtimes. When you first run the program, it's going to generate a circuit. And later, you're going to give this circuit to the quantum computer, and then the circuit would be running on the quantum computer. So the first runtime is circuit generation time, and then the second runtime is circuit execution time. And any kind of data that is known at circuit generation time is called a parameter. And any kind of data that is only known at circuit execution time is called state, okay? And the design choice that we've made in Clipper is that both parameters and state should live in the same syntactic category. They should both be first-class citizens of the programming language on an equal footing. This is not the only possible solution. For example, Quire, developed at the University of Pennsylvania, is an embedded quantum programming language where basically a parameter is any value of the host language, and then state only lives inside a boxing operation. Basically, there are two different languages then, an inner language for circuits and an outer language for parameters. But in Clipper, we decided not to go this route. In Clipper, parameters and states belong to the same syntactic class, and the type of a variable determines how the variable can be used. So this creates certain complications because state in a quantum world cannot be duplicated and needs to be treated linearly. So we need a type system that is based on linear logic. But one of the advantages of keeping parameters and state in the same namespace of the programming language is that this then enables us to create data structures that are part parameter and part state. So an example of this would be a pair of a qubit and an integer. Or, for example, a list of qubits, where the length of the list is known at circuit generation time, so that's a parameter, but then the actual state of the qubits in the list is only known at circuit execution time, so that's state. Now, in addition to this distinction between parameters and state, there's another distinction we also have to make, and it is between simple and non-simple types. A type is called simple if a value of that type only has state and there's no parameter component. So for example, qubit would be a simple type, qubit tensor qubit would be a simple type, but a list of qubits would not be a simple type. And the reason simple types are important is that you can really only box individual circuits. You cannot box families of circuits. So that means when you actually want to generate a circuit and put it in a box, you need to specify which member of the family you're going to box, okay? And that means that circuits can only be boxed at simple types. So for example, an example of a family of circuits is the quantum Fourier transform. There is a family of circuits, one for every n, okay, where n is the number of qubits. And maybe a natural way to code that would be as a function from list of qubits to list of qubits. So if you apply it to a list of 10 qubits, then you'll get the circuit for the quantum Fourier transform of size 10. But the problem is that boxing only makes sense for simple types, and list of qubits is not a simple type, so we need some way of picking out a member of that family of circuits and then boxing that member. And that is exactly where dependent types come into the picture. So now, my co-author Frank Fu is going to tell you about how we use dependent types in ProtoClipper. Frank?
Thank you, Peter. So we cannot box linear functions from list of qubits to list of qubits. which is a shame because a lot of useful quantum algorithms can be given these types. With dependent data types such as vector, we can do the following instead. So first, we take a given natural number n, then we box a member which is a function from vector subqubits of length n to vector subqubits of length n. Now, let me show you how this looks like in the implementation. As we can see over here, we define the dependent vector data types as a simple type. Then we define the quantum Fourier transformation as a families of functions, going from vector subqubits to vector subqubits. Now we can use the box constructs to box the family of QFT functions into a family of circuits. So this QFT box function takes a number as input and returns the circuits of the corresponding size. Here is the circuit that is generated from the QFT box with the input 5. Now that we have linear types on the one hand and dependent types on the other, we'll have to be careful about how to combine these two. And in fact, the most challenging problem of combining linear and dependent types is the following situation. So here we have a linear resource term A. When we give it as an argument to the linear function, the resource term A appears both in term and in type. So how are we going to explain the linear resource get used twice in this typing judgment? In fact, Salvasato and Peng argue that the term A is used twice, so it cannot be a linear resource. So this leads to two different kinds of function spaces, namely the linear function types and the dependent function types. So recently, Conan McBride proposes that we are going to allow the term A to be a resource. But when the resource gets mentioned in type, it's considered we are contemplating the value of the resource. But this does not quite make sense in our settings because, for example, the resource A can be a qubit, and it does not make sense to contemplate the value of a qubit during type checking. So our approach to handle this problem is that we are going to allow the term A to be a resource. But when the resource gets mentioned in the type level, we say only the shape of the resource gets used. And the shape of a resource is considered a reusable data. Let me give you an intuition about the shape of a data. So if we think of data as a tree, then the shape of this data is the same tree structure except that we replace all the leaves with units. So for example, a list of qubits, its shape is a list of units, which is the same as its length. Now my co-author Kohei Kishida will explain the categorical underpinning of our approach. Kohei?
Thank you, Frank. The goal in this part of the talk is to unify the two semantic frameworks for linear type theory and dependent type theory. On the one hand, linear type theory is modeled by certain monoidal categories in which monoidal products are not Cartesian and can therefore accommodate a notion of linear resources that cannot be duplicated. On the other hand, dependent type theory amounts to locally Cartesian closed categories in which every slice over a context gamma is a Cartesian closed category of types and terms in gamma, and the interaction among different contexts is modeled by pullbacks and their junctions. Unification of these two frameworks is not an easy task, however, because on the one hand, LCCCs are, well, Cartesian and do not accommodate the linear notion of resources. On the other hand, monoidal closed categories do not have nice slices, so they do not admit dependent types. Our solution to this problem is to introduce what we call a state parameter fibration, a certain fibration sharp of a monoidal closed category E over an LCCC B. The guiding idea behind this setting is to take an object A of E as a parameterized family of state spaces and its image sharp A or underline A as the underlying set of those parameters or the shape of A. In fact, with a small assumption, sharp has a right adjoint that embeds B as a full subcategory into E so that 1. The role of sharp can also be fulfilled by the unit of a junction, and 2. We can consider slices of E over objects of B. We then axiomatize the fibration so that each such slice is monoidal closed. Indeed, sharp being a fibration means that any map of parameters can be canonically lifted, or equivalently, that any parameter map can pull things back. This slice structure models the dependent types and terms in context and the interaction between contexts. In other words, although not all slices of E are nice, and although E does not have all pullbacks, it is okay because slices over objects of B and pullbacks along arrows of B are enough for our linear dependent type theory. This is actually the semantic counterpart of our principle that dependent types are dependent upon shapes. Let's expand on how the state parameter setting works. Simple types, for instance, boil down to types whose shape is 1. An important idea is that we can think of the lifting of a parameter map or the pullback along the parameter map as reparameterizing the components of the parameterized family A. So pullbacks define linear structures as if component-wise. Using this idea, we can define a functor P that gives to each parameter set the monoidal unit of its shape. When we further assume that P has a right adjoint, we end up with a linear-nonlinear adjunction in the usual sense, and we can use it to interpret the bang operator as well as boxing and unboxing. But maybe more crucially, images of P interpret the parameter types within the category E, thereby placing parameters and state within the same namespace. As another example of component-wise definition, we have a parameterized family of monoidal products here, but then, by getting the subfamily in which the parameters of B depend on those of A, we can define what we call a dependent monoidal product, which interprets both the extension of a context and the linear sigma type. At the parameter level, this is exactly the LCCC interpretation, but at the state level, we are combining resources from the state spaces in both A and B. Using such linear structures over nonlinear parameters, semantics of dependent types and terms goes as follows. First, a context is interpreted by an object of E. Then, a dependent type in that context is an object of the slice category over the shape of that context. A term in the context is then an arrow in that slice category. So this triangle summarizes our interpretation. Observe that if we hit the triangle with sharp, at the parameter level we have the usual triangle for nonlinear dependent type theory in LCCCs. Our linear interpretation, however, is different in that we generally have different objects in the top left vertex and the base. The base needs to be a shape because dependent types depend on parameters, but the top left vertex should not generally be a shape since it may need to embody resources that terms consume. This means that even though dependent types depend on shapes, our semantics still covers the two cases of contexts involving and not involving resources in a uniform fashion, and accordingly, even in linear pi types, the antecedent can involve resources. To sum up, we can say that by taking the fibration sharp, our semantics takes a fibration of the linear type theory of state and resources in the category E over the dependent type theory of parameters in B. So this is how our semantics works, and now Frank will give you more detail on the syntactic side. Frank?
Thank you, Kohei. Now I'm going to explain the syntactic shape operation. This operation is directly derived from our categorical semantics. As you can see here, we are defining the shape of a qubit as a unit. For all the other type constructors, we define their shapes inductively. For example, the shape of a list of type A is a list of shape of A. And the shape of a linear function type is defined as parameter function types from shape of A to shape of B. Now, let's see what our type system looks like once we incorporate the shape operation. If we look at this kinding rule for the linear function type, we first take the shape of A and add that to the context. Then we use the extended context to kind check B. And for the application rule, when we are applying a linear function n to an argument n, we first combine the context gamma1 and gamma2 in a linear fashion. Then we substitute the shape of n into the type B. For this typing rule to consistent, we have to make sure that the shape of n has the type shape of A. And you can find the rest of the typing rules in our paper. Now that we have dependent types, we can do all kinds of new things. For example, here we are defining the with garbage data types. It uses the existential vector data types. The with garbage data type is a monad, and it comes with a round garbage function, so it's just like we have a round function for the state monad. So to see how this with garbage monad is useful, let's take a look at this circuit that is performing the 1-bit addition. So this circuit takes 3 qubits as input and outputs 3 qubits together with a lot of excessive qubits. We will call them garbage qubits. So to get rid of these garbage qubits, we can give this circuit to the round garbage function that come with garbage data type. As we can see here, all the garbage qubits are uncomputed, are collected or uncomputed in a type-safe manner. So here is the circuit that we obtained, and it is the garbage-free version of this 1-bit adder. So to summarize, we make the following contribution. First, we develop a notion of state parameter fibration. Then we work out the operational semantics, type soundness, and safety properties. And last but not least, we have a prototype available on GitLab. So if you are interested, please check out our paper and our implementation.